start with a 2D planar. We're going to call that a bar, which is the part. It's going to be shell. Dimensions are in the millimeters. We're going to say continue, keep the default size of 200, and zoom out a little bit and draw a rectangle by creating line using the rectangle icon. So we're going to create something like this. And then we're going to dimension the horizontal line to be equal to 100. And the vertical line to be equal to 15. All right. So we're going to zoom out and draw a circle, create a little stress concentration hole in the bar. So we draw a circle, put the center somewhere around here to the left, and dimension the circle to be equal to radius of 3.5. And then to locate the center of the circle, we're going to dimension the center with respect to the left vertical edge, and this value is equal to 15. So far so good? Everybody's got that? Dimensions? All right, so we're going to go ahead and say enter and done. You should have the part which is a plate with a hole. So now we're going to define the materials. Okay, so let's go ahead and define material. We called it material 1. Go under mechanical. I'm going to start with plasticity. Define the plastic properties. So the material properties we're going to define are going to be as follows. The first one is 200.2. That's the first stress value, which is your yield stress with the corresponding plastic strain of 0. Enter. The next one is going to be 246, and the plastic strain is going to be 0.02353. Next one is going to be 294. Plastic strain is going to be 0.0474. And next one is going to be 374. Plastic strain corresponding to that is 0.09354. And 437, 0.1377. Notice the strains are getting a little bit larger. Finally, 480, plastic strain of 0.18. These are the uniaxial tensile test properties. And I am going to go back to elastic and define the new Young's modulus, which is going to be 210,730. With a Poisson's ratio of 0.29. As you can guess, this is probably some kind of a steel that we are using. All right, so remember we're solving a plane stress problem. We're going to go under the sections, define a plane stress, and this is going to be 5 millimeters, so I'm going to type that in as well. Solid, homogeneous, continue. Check the plane stress strain thickness, give it a value of 5. All right, assign the property, don't forget that, assign the section to this whole thing. I'm going to undo the create set, say done, assign the section property, see the color green appearing. Then create instances of this assembly and say OK. Now we're going to go ahead and do the step. This time we're simply going to load the problem in a ramp mode, not worry about unloading. So we're going to create a plasticity step. Say continue. Time period is going to remain as 1, meaning we're going to go from 0 to maximum load corresponding to time period 1. Incrementation, Notice initial and maximum are the two that you want to incorporate and manipulate. The initial, I'm going to change that to 0.05. Maximum, I'm going to change that to 0.2. And let's see what happens. All right, and say OK. Under field output, I want to get a more detailed representation of the field output. If I don't, the program will automatically use whatever automatic incrementation that you used and uses those values to output the data. If I want a more refined data, I'll go under field output 1. Instead of every n increments, I change that to perhaps every x unit of time and make that 0.01, meaning from 0 to 1, which was the maximum load. How many data points am I going to extract? 100 data points. So my plots, whatever it is that I want to do, is going to consist of 100 data points. If you don't do that, you do that based on the automatic n increments, you may get just 20 data points. You may get just the jagged line as a result of it. I'm going to uncheck contact, which is unnecessary in this case, and say OK. All right, so we've done the output creation. First thing I want to do, start with a boundary condition. I'm going to fix the far end. Since this is a plane stress, I'm going to pick the displacement rotation and call that the fixed end. Continue, pick the vertical edge on the left and say done. And pick U1 and U2 and set them equal to 0. Okay, get ready for the loading. Now, what I want to do with the loading is that I want to apply a transverse or shear load, if you will, to the right vertical edge, except that I want to do that in a quadratic form. Meaning what? Load is going to be the maximum at the very top, drop to 0 quadratically in the center, and then move back up to the maximum toward the bottom edge. Do you understand what I'm getting at? In case you don't, I can try to draw this for you. All right, so what I'm going to suggest is the loading that is going to look like this. Maximum here, right? Maximum here, 0 in the center. So your loading is going to look something like this, right? If you want to plot that, that's what the distribution is going to look like, except that it's going to apply in the vertical direction, right? So flip that over, if you will, 90 degrees. That's how you're going to apply the load in a quadratic representation. As you're doing that, you have to be careful about how you implement the coordinate system. So I want to define a coordinate system so I can attach the function that I'm going to define to that coordinate system. So where do I define a coordinate system? Let's go ahead and create a datum coordinate system with 3 points. The icon that you see that I've highlighted, it's going to be the rectangular coordinate system. I'm going to call that shear load coordinate system. Continue. And luckily for us, we have the center highlighted as a point. So I'm going to pick that point as the origin. It is asking me to define a point to be on the x-axis. You can define it in any way you like to. I am going to, let's see. Since I want to define that as a function of x, I want to go ahead and pick the vertical bottom edge point as the x, and any point on the y, I'm going to pick maybe this point to be along the y. Be sure to cancel now, otherwise you're going to create another coordinate system. Have you defined this coordinate system? Yes? Good. Give me some feedback here. All right, we defined a coordinate system. Now I'm going to define a field. Okay, so double click on the field, open it up, you have two options, the discrete field or analytical field. I want to define an analytical field, meaning I want to define a function. Double click on analytical field, I'm going to call that a quadratic function. It is based on an expression that I want to type in and say continue. Now you will see something very interesting happens. You bring up a dialog box whereby you are given some operators, plus, minus, multiplication, division, pi, etc., etc., etc. If you want to do the exponentiation or raising something to the power, you use this one that is called power parentheses a comma b. Don't do anything with it yet. Now, remember, I want to define my function with respect to the newly defined coordinate system. So I want to change my local coordinate system to what? From global to the local coordinate system. So click on the edit or the arrow on the local coordinate system and highlight the global system you defined. Click on it, and that should show that shear load coordinate system. All right. Notice the parameters that are available to you down here, x and y. Do you see them? So I'm going to go ahead and say, click on the power. First, be sure that it is in that field where you type your expression. Click on the power of a and b. You see POW and then parentheses shows up. In here, you simply click on the x. Notice I click on the x. And then comma, you type in comma 2. That means I want to take the variable x, raise it to the power of 2. But the variable x as defined by what? My local coordinate system. Right? Did you do that? And we'll say OK. Now we're ready to apply the load. Okay. The load that I want to apply is going to be a shear load. So it's going to be a surface traction. So we're going to call that shear traction. Continue. Pick the surface, which is going to be the vertical edge on the right, and say done. The dialog box appears. First things first, distribution is no longer the uniform, right? Because you defined a function, click on the down arrow. Do you see the quadratic function as the last entry that you created? Simply click on it. Traction is going to be shear. Vector before projection, it says required, meaning you need to define up, down, or what direction. Click on the arrow. Pick maybe this point as the first point and down here as the second point. That shows the direction. Then the value of magnitude is going to be equal to 0.8. Can you tell me what that unit is? Traction is defined per area. So this is going to be in the unit of MPa, a megapascal. Can you convert that to the actual load that is being applied? You have an area, right? You have the length, you have the thickness. The maximum value, at least you know what it is. Clearly that is not the total load because the load is going to vary quadratically. And we will say OK to this thing.
Question?
Yes?
Do I need to change the CSYS?
You have to.
It's global.
So shear traction, what do you mean see it?
Yeah.
Oh, this one?
Yeah.
No, that is the vector where you define the direction of the load. Okay, so don't touch that one. Okay. Now, unfortunately, the arrows that you see don't quite do the justice to you because you only have two arrows showing. One of them is at the very top, the other one is at the very bottom. In reality, that's maximum, somewhere in the middle is supposed to be 0. Some other computer programs allow you to define that as 10 arrows instead of 2 arrows, in which case you can see the gradation, maximum gradually reducing down to 0, then increasing again. But in this case, you have to trust what we have. Any questions so far? All right. So let's go switch to the mesh. Switch to the part. Click on the assign mesh type. We're going to make sure it is set for plane stress. We're going to uncheck reduce integration. Do we need to do incompatible mode or not? Do we need to do incompatible mode or not? Why are you saying yes? Primarily bending is taking place here, right? Okay, so we're going to go ahead and say incompatible mode and OK. And then we're going to assign mesh control. Now, since you have the hole in the middle, we're going to have to do a medial axis mesh with a quad only. And then change the distribution from 9.9 to maybe 4 and do apply and see what the distribution looks like. That's too small. I mean too large. We make it 2. That's a little bit better. We'll mesh the part and see how many elements we created. We created 385 elements. Is that what you got? Something like that? How many elements did you guys get?
405.
405 is good enough. Does it look like that so far as the medial axis part is concerned? All right. So let's go ahead, create a job. We call that solution of plasticity for bar. Continue. And don't forget to save the work. Okay. So far, so good. We've saved the work. We're going to right click on this thing and do submit. And I'm going to go to the monitor section and bring up the monitor, enlarge that if you can, and drag that thing down so you can see the incrementation. The first thing I want you to pay attention is that the incrementation is always going to be 0.01. Why? Because that's what you told the program to print out the results. If you had set the default output, you would see the variation on those incrementation rather than just 0.01. Now I want to show you the warnings. These are the things that I would call informational warning rather than the warning that something is wrong. Can you read them for me? The first one says, for two-dimensional model, if a non-unity thickness is specified for two-dimensional solid elements, and these elements are involved in interactions such as contact, then the thickness have to be compatible with the contacting element. I don't have to worry about that, right? The second one says you've defined output at the exact specified point, so blah, blah, blah. Don't pay attention to that either. Okay, so I'm going to say right-click results. That's the step time 1, meaning the final load step. Look at the deformed shape. This is the von Mises stress. I'm going to switch to the PEEQ, which is what? Plastic strain, right? Do you see what the maximum plastic strain is in this case? What is it? About 0.19, right? Okay. Sometimes this is not really that important to you. You want to see the nonlinear behavior of this thing. In other words, you want to look at the displacement and perhaps the displacement in the vertical direction. And somebody wants you to plot the movement of the maximum displacement as a function of what? You remember load versus displacement function? After all, you want to prove to somebody that you indeed have nonlinear behavior in your system. Okay? So let's see what we can do here. I want to go ahead and plot that in the undeformed shape. Are you with me? So we're going to go ahead and under this icon, which is called Create XY Data, click on that one. And the default is for history output. We're going to switch to the field output instead. ODB field output. And say continue. And you notice it automatically switches to integration point because it assumes you want to look at the stresses and related quantities where you look at integration point such as strains, etc. Except that I don't want to look at the integration point. I want to look at something called unique nodal because I want to look at the displacement. And now suddenly things change. You have a lot more options available to you. Instead of checking the spatial displacement, I want to click on the arrow to make it a down arrow and go down and pick U2. That's the only thing I want to plot. Otherwise, you get a whole bunch of plots. Things become confusing. Don't do anything. Don't say plot yet, because you have to tell it what are you going to plot. Okay? So then you go on the tab that is called Element Nodes. The default is pick from viewport, which is what we want to do. Notice it says click edit selection to pick in viewport. So we're going to do edit selection. The prompt says to select the node for the display group. Which one you want to pick, either the top one or bottom one. It doesn't really make that much of a difference. I want to pick the top one. And say done. And you notice in the XY data window, it says one node has been selected. Now you're going to say plot. And some bizarre looking plot appears. Why is it bizarre looking plot? Because it is showing you displacement as a function of time. Can you tell me what this time corresponds to?
Percentage of load.
Percentage of load. Very good. All right. So you want the load increment as a function of the displacement. So what do I need to do in this case? I need to reverse this thing, correct? Not only that, because of the negativity of the displacement, things are going to be really bizarre so far as the plot is concerned. I'm going to give you a very easy option that is available in Abaqus to be able to export the data to something like Excel and use Excel to do the plotting for you. All right? So I'm going to go ahead and dismiss from this thing, go on to something called XY Data Manager. Okay? So you go to XY Data Manager. You have the name of your file, that is the plot file, except that you say edit, and a scary looking thing appears, which is your actual data point. One more trick up my sleeve. If I copy that,
It lets you copy one by one.
one by one. Okay, so I'm doing one at a time then. One column at a time. Okay. I promise you I did that at the same time in my office, but that's okay. So we've copied these data one column at a time to Excel. Keep in mind what these things are. This is the load increment. This is the displacement. The displacement being negative is going to cause you some problem, because if you plot it, it's going to be the mirror image is what you want. Is there. So now what do I do with this square?
Just double click.
Okay, thank you. Okay, so we're going to go ahead and plot. Insert chart, right? What kind of chart do I want? probably just a line chart instead of data points. I don't want to see all these data points. And right click here and do select data, add series name. We're going to call that load versus deflection. Series X. What do I want on the X? Excellent. You guys are good. And this one I click on what? A? And say OK. OK. And I believe that's my load versus deflection plot. I want to plot something more interesting than this. So let me go back to my undeformed shape again. And I'm going to switch to plastic strain. Do you realize where the plastic strain is becoming the maximum value? All right, around here somewhere, right? So now I want to go ahead and do create another plot. Create XY data, ODB field output, continue. Maybe you can still do the unique nodal, which is fine. And PEEQ is what I want in this case to plot. And go ahead and pick element and nodes. Pick from viewport again, edit selection, highlight that point and say plot. Why do I have two plots? Because I didn't tell it not to plot the vertical displacement. So that one is still there. How can I manipulate that? Go under variables, go down below, uncheck this thing and say plot. Now what you have is, by the way, if you don't like the color of this thing, just click on the plot again and some other color will show up until you like the color that you see the color that you like. So this is a very nice visual feedback for you to see at what time increment, which is at what load value in reality, does the plastic strain initiate. And then what the maximum value is going to be, and you notice the nonlinear behavior of it as well.